Welcome to Lab 7. Lab 7 has to do with the topic of implicit differentiation. So first it's helpful to know what is an implicitly defined function. Implicit functions are not solved for y, and this is because that's usually a difficult thing to do. If you look at the example down below, you've got two terms with y in them, and you're not going to be able to get that down to just a single y. So functions that are solved for y, like a line, the typical equation is y equals mx plus b. That's an explicitly defined function. So when your variables are all kind of mixed up together, we do implicit differentiation to find the derivative. And there's four basic steps in the process, which I have outlined at the top here. But we'll go through an example just to remind you of what implicit differentiation looks like. So in this case, I look at my function. Again, I notice the x's and y's are all kind of bound up together, and I'm not going to be able to isolate them. The first thing I'm going to do is a little bit of notation where I just indicate that I'm going to be taking the derivative of the left side and the derivative of the right side. Now, when you're taking the derivative with respect to x of a term that has an x, you can just do the usual power rule. So you take the exponent, multiply it by the coefficient in front, which gives me a 9x, lower the exponent by 1. When I need to take the derivative with respect to x of a variable that does not match, say in this case the y, I'm again going to start with power rule. So I'm going to get 21y squared. But you always have to put a dy dx next to any term where you've taken a derivative of y. On the right-hand side, again, I notice my variables here don't match. I'm taking a derivative of an expression in terms of y, but I'm taking the derivative with respect to x. So I take the derivative of 10y. The y is going to disappear, giving me just the constant 10. And again, because I took a derivative of a y term, I'm going to put a dy dx. I'll have my answer if I can get dy dx by itself. So the first thing you'd want to do is gather them all on one side. I'm going to leave the 9x squared on the left side of my equation. I'm going to move the 21y squared dy dx by subtracting it on both sides. So on the right, I will keep the term 10 dy dx, and I'll subtract 21y squared dy dx. When you change what side of the equal sign a term is on, you change its sign. Now I'm going to factor that dy dx from both terms on the right. That would look like that. And since I want dy dx to be by itself, and right now it's multiplying this binomial, I'm just going to divide to get rid of the binomial. And so my final answer is dy dx is by itself now. And on the other side, we have 9x squared over 10 minus 21y squared. So again, notice the derivative still has both variables in it. That's implicit differentiation. I'm going to now show you how to use Mathematica to perform implicit differentiation and how to graph implicit equations. Suppose, for example, we want to find the derivative of this implicitly defined function. The command you use in Mathematica begins with the capital D for derivative, and you're going to type in your equation with a slight modification. When I come upon a y in my original equation, in Mathematica, you need to indicate that y is a function of x. And that's exactly how you would do it. In place of the equal sign, double equal sign. Then, when I have to do 4y cubed, again, I have to indicate that y is going to be a function of x. And I can put my exponent on that, no problem. So there's my function. After that, you just need to let Mathematica know what derivative you want to take. So we're taking a derivative with respect to x, and it's the first derivative. You get this output in an implicit format. Notice you have the derivative y prime on the left and you have the derivative y prime on the right. We want y prime typically to be on one side of the equation by itself. So to do that, I'm going to use the solve command, and I'm going to put a percent in the first spot. What a percent does is tells Mathematica, please use my last output. So I don't have to retype it all, I don't have to copy and paste, I can just put the percent there. And after that, I'm going to put what I want to solve for, which is y prime of x. The format here looks a little different, again, because it's got these y as a function of x statements. Compare that to how it would normally be written. Okay, these two statements say the same thing. Mathematica, again, has to have that y as a function of x clearly defined. But if you were to write it down, there would be no need to do that. Now, the second thing we're going to cover is just how to graph those implicit equations. Graphing an implicit equation by hand is a little bit of a challenge and not something you've typically done. But Mathematica can handle that no problem. So I'm taking the same implicit function I used in the first example. And notice, again, this is the original equation. I'm not graphing the derivative. I'm just trying to see what the original function looked like. And I'm given a domain and range. In order to do this, you don't use the plot command. You use the contour plot command. Square bracket, of course. And notice when I type in my function here, since I'm not taking a derivative, I don't have to declare my y as a function of x. I've typed in my function in just the standard way, but with that double equal sign. After that, I put a set of set brackets defining the domain I want to see and the range I want to see. Now, if you hit Shift and Enter, you're going to see this is actually what the graph does look like. But you're going to notice that the scale numbers are put on the outside of the graph, and there's no indication of where the origin of the graph actually is. In other words, the axes are not there. So I'm going to go back to my plot command, and we're going to add the command axes with an arrow true. Axes true just tells it to put the axes in there. So now I can see that this function is passing through the point 0, 0. And that's how you graph implicit equations.